Here's the problem. Solve x minus 3 times 2 minus x times x plus 1 is less than 0. It's an inequality, and it's an inequality with a polynomial function. So the way I'm going to show you this, we're going to build on what you just learned about the graphs of these polynomial functions, because we can just, if you can sketch this, then you can just simply read off the answer to this problem. I find this to be far easier than how the textbook shows you. Now the textbook method is good, and certainly nothing wrong with it. What it does is that you find these roots, and the roots are 3 and 2 and -1, and then you pick a number in these intervals that are in between or on the outside of these roots, and you plug those numbers in to see if your product comes out to be less than 0 or greater than 0. And when it's less than 0, that's part of the solution. So it's a testing method, a trial and error testing method for solving an inequality. Perfectly valid method. It just takes more time than is necessary. Because what if you knew the shape of this graph went like this? All right. In other words, if we said, well, let's look at y equal to x minus 3, 2 minus x, x plus 1. All right, it's a third degree polynomial. The leading coefficient is -1. In other words, this would be negative x to the third. And here are the roots, so it has this shape. And the, here we go. And the y-intercept, incidentally, would be, let's see, -3 times 2, -6. -6. So I kind of went backwards here, but suppose we sketch this, y equals to this function, on the graph. And if you can do that sketch well, then the solution to the inequality problem is the same as finding out where is y less than 0. Well, where is y less than 0? It's down here, isn't it? Why is there negatives down here? Y less than 0. Down here. All right, so where is the graph less than 0? Between these 2 points, it drops down, and here it drops down. So that allows me to write the answer to the inequality. Okay, this function is less than 0 when x is in the interval from -1 to 2, or the interval from 3 to positive infinity. There we go. That's the solution to that inequality. X has to lie between -1 and 2, or it has to be greater than 3. And we're done. So that's the idea here. Build on what you learn about the behavior of functions, and then we can use it to analyze an inequality and solve it rather quickly. And so now I said the textbook technique is good. You know, I don't want to criticize it at all. It's a more general technique that works for all kinds of functions. You know, if you want to solve an inequality of any function, if you can find the roots and put them on a number line and test in between, then you're going to be able to solve that inequality. And but I'm only worried about polynomials here. That's why I'm showing you this very fast technique to build on what we learned about polynomial functions. The textbook technique, if you take calculus, you're going to learn that. Okay, I guarantee, because we face things other than polynomials in calculus, and so you will get exposed to that technique there. All right, well, I'm going to erase the board and do 1 or 2 more quick examples. Here we go. Solve x minus 3 times x plus 1, x minus 3, 5 minus x, greater than or equal to 0. All right, now I'm going to use the same technique. I'm going to think about this as a polynomial function, and if I did, y would be negative x to the 4th plus stuff. All right, because we have x times x times x times negative x. So So that means it's a fourth degree polynomial. It's upside down, shaped like an M. And the roots are x equals to 3, minus 1, 3, and 5. So we have a repeated root there. We're going to have that, polynomial action near that root of 3. And the y-intercept, let's see, it's going to be negative 3 times 1 times negative 3 times 5. That would be 45. It's a positive number. All right, so let's sketch that out. And let's see, positive 5 is a root, and so is 3, and negative 1. And this is my shape, and it's repeated at 3, so it's just going to touch. So my graph is going to, I think it's going to look like this, or it has to hit these 4 points. So it comes up, whoops, comes down, just touches, comes up, and comes down. All right. I can be a little sloppier when I'm solving an inequality because the point of the problem is not to sketch the polynomial nicely for someone else to read. The point of the problem is to solve the inequality accurately. All right, so, but, the point is that by sketching the graph, we can identify the behavior of the function. And that's the nice thing about graphing. Graphing allows you to see how a function behaves. What are its characteristics, and that becomes a bigger and bigger issue as you move up the mathematical food chain. When you go into calculus, you'll learn all the techniques there are to graphing, and by examining those graphs, you can tell how functions behave, and that gives you a lot of good insight and good information into applications that are described by those functions. And by the way, the process of describing those, the application with a function is mathematical modeling. So all this kind of begins to fit together after a while. All right, where is y greater than or equal to 0? All right, in other words, where this is greater than or equal to 0 is above or touching the x-axis. So it could touch the x-axis, and it's looks like everything between minus 1 and 5 inclusive. So the solution to my problem, x would have to be in between minus 1 and positive 5. And I use the brackets there. So, okay, I think I'll make this my last example on this for the video. I got some more in the book if you want some more. But in my experience, people pick this up very quickly. Once they understand sketching well, then doing the inequality is almost a no-brainer, okay? Because this is a matter of looking above the graph or below the graph, depending on whether it's greater than or less than. And so there we go.